So if you're funneling back, welcome back. We're just gonna have another moment or so before we get started on the last session today. Okay, so it's 10:45. I suggest starting on time is probably a good idea. And it looks like we have a good collection of folks. And so, I expect a few more to stream in. Welcome to the last session of SAZERAC 2. This one is largely dust themed. So it's my pleasure to help moderate the session with Pascal. And our first speaker today is Rebecca Bowler, who will talk about the diversity of dust geometries in UV bright galaxies at redshift 7. So Rebecca, how about you? Go ahead, share your screen. Yeah, perfect.
Hi, you can hear me.
Take it away.
Perfect. Yes, thank you so much. It's a real pleasure to be able to speak at this lovely conference this week. So, as Caitlin said, the title of my talk is The Diversity of Dust Geometries in UV Bright Redshift 7 Galaxies. And this is a work in preparation with these co-authors listed on the slide here. So as I have the privilege of being the first speaker, I thought I would motivate my talk by giving a kind of overview of some of the many open questions we have about dust in the epoch of reionization. And this is all kind of built on the back of this kind of new regime of detecting very high redshift galaxies using the power of ALMA, which has led to an increasing number of dust continuum detections at redshifts greater than 6. So we want to understand what is the dust production mechanism. This is really fundamental. And part of this is understanding what is the dust temperature, which is currently still quite unknown at these redshifts. And this is all crucial for understanding how much of the star formation at these redshifts is obscured. And this is a nice plot from Caitlin Casey's work, which shows you some of the huge uncertainties we have in this high redshift universe when considering the cosmic star formation rate density. And this is due to our unknown dust properties. So another fundamental question is, what is the geometry of the dust relative to the stars? This is important in particular for energy balance, where you often assume these things are mixed, but is this really true at these high redshifts? And the problem with understanding this question at very high redshifts is that the majority of galaxies we know of at redshift 7 or so are extremely compact in Hubble data. And even with James Webb, they're going to be barely resolved. So the solution I propose to this problem is to look at the very brightest sources we know at redshifts around 7. And as you can see on the right here, with the size luminosity relation, the very brightest sources are highly extended this is Hubble data measurements. And this allows us to really look in more detail at the morphology of the dust relative to the UV emission. So if we look more closely at these 6 galaxies in the blue box, these are the 6 objects that I'm going to be talking about today. And they're the brightest redshift 7 galaxies in this plot. And you can see that with this single band Hubble data we have, that they break up into multiple components, several of them, and they're all resolved with Hubble nicely. A couple of these are spectroscopically confirmed in the literature, and the other 4 are targeted by rebels. So this is a little prequel to Sanders' talk coming up later today. So these are the 6 galaxies that I'm proposing for follow-up with ALMA. So we did look at these a few years ago with quite short integration times, just 10 minutes per source in band 6, to identify any dust continuum emission. And we detected one source, which is shown on the bottom left here in this data. So we wanted to dig a little bit deeper. So in cycle 6, we got much deeper observations, 120 minutes per source of the 5 undetected objects. And you can see the results of this in the panels on the bottom. So the background is the Hubble data, which is the rest frame UV, and the contours is the dust continuum emission from ALMA. So it's great that we got these detections, but the real power of this new data was that it has higher resolution than previous observations. So previous observations have had resolutions of of around 1.2 arcseconds or so. But this data, we asked for a slightly higher resolution of around 0.7 arcseconds. And this allows us to pinpoint the centroid a little bit better and compare it nicely to the ultraviolet emission. So this is just an example. If we zoom in on this source with the two components, the dust is now, we can see that it appears to be offset from the centroid of the UV emission. So we found several different kind of morphologies of the dust. We found some quite compact emission, and this does appear in several cases to be offset from the UV centroid. Now, of course, when you make these comparisons, you have to be very careful with the astrometry. So I've done a lot of checks. All of the imaging probing the UV emission is matched to Gaia to very high accuracy. And the ALMA data, the real limitation here is the fact that these detections are only around signal to noise 5. So we expect the error to be about 0.1 arcseconds on the position. But we do think that these are physical offsets that we're seeing here. In addition, we see evidence for elongated dust emission that's co-spatial with the ultraviolets. For example, in this case, the ALMA measurement splits into 2 clumps, which seem to be aligned with the rest frame ultraviolet emission. Okay, so now I'm going to focus in on this one particular source. So this object is at redshift 7.06, spectroscopically confirmed by Sander, and it's one of the brightest redshift 7 galaxies we know of to date, minus 23 UV magnitude, and it's clearly highly extended in the UV. So we only have single band Hubble data for this object, but when I was compiling the imaging for this object, I noticed that in the ultravista multi-band near-infrared data that there appears to be an offset between the different wavelengths. So of course I checked the astrometry and there's no relative astrometric problems between these two data. This appears to be a physical offset. So the blue contours here show you where the Y band sits, which is probing the far UV part of the spectrum. And the red contours show you where the ground-based K band sits, whereas this is a kind of much redder UV probe. So you can see that there appears to be different centroids for these different wavelengths. So I went further and made a color map, and now you can clearly see that there's a color gradient across this source, as observed in the PSF homogenized ground-based data. I went further again and measured the UV slope from this multi-band data, and you can again see a gradient, as you might expect, in the ultraviolet slope. So how does this color gradient we see in this source correspond to the dust continuum emission that we detect? And I've already shown you this, but here it is again. And in this sort of scaling, the background here is the ALMA data. That white blob is the dust continuum centroid. So you can see that we observe this clear gradient in the rest frame UV colors, and it appears to be pointing in the direction of the dust continuum detection, as you might expect. So this was really exciting, and we went one step further to extract photometry for each clump. So for this, I used a deconfusion analysis using the TFOT software, where the high resolution image is our single band Hubble data, and I then used this to deconfuse the low resolution YJHK data from UltraVista. And in this analysis, you can clearly see again the 2 different colors of the 2 different components pointing towards this dust detection in the upper left of this image. So I don't have time to present the rest of the sample, but just to give you a very quick preview, and of course you can pause this if you're watching the recording, we do observe gradients in the other 3 sources where we have a strong ALMA detection, and this is really indicating that this is quite a common effect in these high redshift bright sources. So what are the implications of this color gradient that we observe and the dust offsets we see relative to the kind of centroid of the UV emission? Well, this is telling us that the brightest and bluest position in the ultraviolet is not representative of the full galaxy. For example, the size of the source is not just this lower clump, it's the whole object. It's likely not showing us the center of mass of the source. And if we were to infer a dust attenuation AV value, it wouldn't be representative of the full galaxy. So this has been seen many times before in the literature at lower redshifts and also to high redshifts as well in the submillimeter community, where essentially the different wavelengths probe different parts of the galaxy, of course. So in this nice example from Redshift 2, from Target et al., this is a dusty galaxy where the dust centroid is in the center of this stamp. But in the UV emission, exactly as we observe in these high redshift galaxies, the source is only two tiny blobs you see either side. As you go to longer wavelengths, you start to see that, in fact, the center of mass of this source is actually where the dust continuum peak is. So in this right-hand plot, you can see the full galaxy is actually much more extended relative to the UV. And this is also nicely shown in this plot from Rachel Cochrane's paper on the right, which is from simulations, which shows you that the far infrared and the UV morphologies are completely different. And in fact, the whole galaxy is much more extended than you see in the UV. And the far infrared peak is again offset from the ultraviolet emission. So I'm almost out of time, but just to wrap up then, what we really need is redder imaging for these high redshift sources. And of course, you know what I'm going to say next. This is exactly what we're going to get with James Webb. And I see this as a very exciting preview of the results we're going to get from James Webb, where we're going to be able to really measure this kind of longer wavelength part of the spectrum at high resolution for the first time. And as my very final point, I'm going to just kind of pose the question, are we seeing just the tip of the iceberg with ALMA and Hubble? And in fact, when we look deeper with James Webb, we're going to see a much larger extended component to this source, where we're only seeing the very unobscured parts pop out in the UV. And again, the very brightest part in the far infrared. And with that, I will end and take questions. Thank you.
Great. Thank you, Rebecca. I will give folks 20 seconds or so to type up questions on Slack. So Pascal, do you want to?
Yeah, I can do. Yeah, there's one question already.
Yeah.
The question is from Maruja, and she's saying, "Great talk. Do you have an indication of how much more extended the dust continuum is compared to the UV? It was hard to read the labels."
Do you have a particular slide in mind? I mean, oh, for the extended dust emission, you mean early on? I mean, it seems to be similar in spatial extent to the ultraviolet emission. It's not much larger. And in fact, there's been other studies that show that usually the dust is more compact than the UV emission. And I think you can kind of see from this nice simulation on the right why this might be, because our far infrared observations are not going to be deep enough to see the full extent of the galaxy, these kind of fainter, wispy parts of star formation. They're only going to pick up the very central starburst.
So we have another question. From Justin, any thoughts on how the differential distribution of dust might influence some of the SED fitting assumptions that we all usually make, particularly in using energy balance codes like UV plus IR?
Yeah, it's a great question.
Big question.
I think I have to think about this more and maybe reply fully on Slack, because it's obviously a big question. But I mean, essentially, you could break the source into three separate components with very different dust properties. And also there's some measurements of the fact that the dust temperature changes with star formation rate or infrared luminosity. So also you may have to take that into account, that these three things could have very, very different properties. And also, in my kind of exaggerated disk of stellar mass here, the metallicity could definitely be different across the surface as well. And how that impacts the dust composition, I mean, we really just don't know that. So. But yeah, I can reply more on Slack.
So there are a couple of other great questions too. Do these bright LBGs at Redshift 7 have Spitzer detections?
Yeah, that's a great question. Yes, so they do. Unfortunately, the one I'm showing you the most of on the left here, it's quite confused with a low redshift galaxy just below. So it's really hard to tell if the Spitzer centroid, you might expect it to be kind of offset to the UV part. So it is not, you can't really tell from the current data. And for the other sources, unfortunately, the UV components are too close together for the deconfusion to work. We just need JWST to do this, basically.
So now might be a good time to transition. There are more questions in the Slack, Rebecca, if you can answer them. So next up, we have Minghao Yu sharing results of ALMA observations of sub-kiloparsec structure of the host galaxy of a redshift 6.5 lensed quasar.
All right, thank you.
Do you want to share your screen?
Yeah, let me share my screen. So, and start showing the slide. So
Great.
Can you see the slide and can you hear me?
Yes.
Okay,
Perfect.
great. So can I start now?
Mm-hmm.
All right. So hello, everyone. This is Minghao Yue from the University of Arizona. I am a 5th-year grad student working with Professor Xiaohui Fan. And first, let me say thank you to the organizers to give me the opportunity to make this presentation. And today I'm going to talk about our recent studies of a truly unique and interesting object, which is a gravitationally lensed quasar at redshift 6.5. So this quasar, J/39, was discovered by our group a couple of years ago, and is so far the only known gravitationally lensed quasar beyond redshift 5. So here I'm showing the optical to near infrared spectrum and the HST images of J/39. We can see from the HST images that J/39 is clearly resolved into multiple components, including the foreground diffractor galaxy and the lensed images of the background quasar. So the best fit lensing model suggests a magnification of 51. Such a high magnification makes J/39 one of the brightest quasars at high redshift in all wavelengths. And lensing also allows us to reach a high spatial resolution on the source plane, making J/39 an ideal case study of high redshift quasar population. In this talk, I will focus on the recent ALMA observations of J/39. So the ALMA program contains 2 parts. The low resolution part, aiming at measuring the overall properties of the quasar host galaxy with high signal-to-noise ratio, has been finished in 2018. And the high resolution part will capture the small-scale structures of the quasar host galaxy and has only been partially executed. Well, hopefully it can get finished after ALMA resumes operating. And this talk will focus on the low resolution data, and with a beam size of about 0.3 arcsecond, the lensed arc of the host galaxy is already clearly resolved in the low resolution ALMA image. We also extract the C+ line emission line of J/39, and it shows a regular Gaussian profile and an ordered rotation-like velocity field. According to the best fit lensing model, lensing magnification boosts the physical resolution on the source plane to about 0.8 kiloparsec, which is sufficient to well resolve the quasar host galaxy emission. So we fit the continuum and the integrated C+ emission line as SAZERAC profiles, and we find that both of them can be pretty well fitted by a SAZERAC profile with index around 1. In other words, the host galaxy of J/39 is basically an exponential disk. We also construct the source plane moments for J/39, and as you can see here, it clearly shows a rotation-like velocity field. These features suggest that J/39 is a rotating galaxy with a regular profile, and it's probably not an ongoing major merger. The reconstructed source plane moments actually reveals many interesting aspects of J/39. So the first point I want to discuss here is the C+ gas kinematics. Well, we can look closer at the source plane moment 1 map and the position velocity diagram. Again, both plots show features of a rotating system. For example, we can see the rotation curve on the PV plot. So with the rotation curve, we can estimate the dynamical mass of the host galaxy. I mean, one thing to notice is that the rotation curve itself cannot constrain the inclination angle of the rotation axis. So that's why we have a sine I term in our result. We also get the black hole mass from the near IR spectrum, with which we can estimate the black hole to host galaxy mass ratio. This ratio for J over 39 is significantly, several times larger than indicated by local relations. And this so-called overmassive black hole phenomenon is quite common and well known in high redshift quasars. There are many plausible scenarios for this, from an early supermassive black hole growth relative to their host galaxies. And some other people also suggest this is a pure selection effect. And here, a careful analysis of J over 39 shows another possible reason for the overmassive black holes we see in high redshift quasars. So to illustrate this, we fit the C+ emission as a thin axis symmetric rotating disk. It turns out that a rotating thin disk model fails to describe the C+ emission in J over 39. The main reason is that the velocity gradient, which I mark as the black line here in the plot, is not in the same direction as the flux major axis. In contrast, we can imagine a tilted thin disk model where we'll expect that the two axes should have the same direction. We also go through the literature from which we find that many other high redshift quasars have similar misalignments, similar plots to J over 39, which I'm showing here. So in other words, J over 39 and probably many other high redshift quasars have a gas kinematics that is more complicated than a rotating thin disk. One consequence of this is that we'll have some significant systematics when estimating the dynamical mass. If we look at the moment 2 map of J over 39, the velocity dispersion is about 80 kilometers per second. Such a high velocity dispersion will almost certainly lead to a thick geometry. Well, this could be the reason why a thin disk model doesn't work. And since the turbulence can support the galaxy against gravity, there will be an additional term in the dynamical mass estimation, as I'm highlighting here. So if we use only the rotation velocity to estimate the dynamical mass, the result is likely underestimated. In other words, one possible explanation to the overmassive black holes we see in high redshift quasars is that we are indeed underestimating the host galaxy mass. The analysis of J over 39 thus illustrates the need of a careful modeling of high Z quasar host galaxy dynamics to fully understand this question. In the case of J over 39, we realize that the current data still doesn't have enough resolution for a detailed dynamical model, and the upcoming high resolution data will provide more information. Another interesting point is that J over 39 is an extreme star forming system. We estimate the star formation rate using the far infrared SED and measure the molecular gas mass using the CO emission lines. J over 39 has a pretty high star formation rate, and correspondingly, it is very gas rich. The gas mass fraction is estimated to have the order of unity. So we can compare these values to some theoretical limits. I listed 2 limits here. The first one is the Eddington limit of the star formation surface density, which corresponds to the maximum gas collapsing rate limited by the radiation from existing stars. The second one is the freefall limit, which is basically the gas collapsing rate corresponding to the freefall timescale. If we compare these 2 limits to the observed values, we'll find that they are pretty close to each other. In other words, J over 39 is forming stars at the maximum possible rate. So that is what I mean by an extreme star forming system. So we want to ask this question: what triggers the intensive star formation in J over 39? Well, when talking about strong star formation, one obvious thing to consider is gas-rich major mergers. In the case of JL439, however, as we discussed earlier, it has a regular shape and a rotation-dominated velocity field. It's probably not an ongoing major merger. If the star formation is indeed triggered by a merging event, the only possibility would be that JL439 is the remnant of a recent merging event. To confirm this, we need to seek for signs of a recent merger, like irregularities in the host galaxy, and hopefully the upcoming high-resolution ALMA data will do this. And another possibility is strong cold gas inflows from the CGM. This is also a mechanism that has been proposed by simulations for a long time. Given the large gas reservoir in JL439 and with the help of lensing magnification, it will be a very interesting thing to look for cold gas streams around JL439 using deep imagings of, say, CO or C+ emission lines. And finally, let me talk more about the high-resolution data that is upcoming in probably the next year. As I mentioned earlier, the high-resolution part of the ALMA program has been partially executed, and here I'm showing the data that has already been collected by the program. With the high-resolution data, we will solve many of the remaining mysteries we mentioned in this talk. For example, we will build a better lensing model for JL439 and will perform detailed dynamical analysis of the host galaxy. I mean, to me, the most exciting thing is that the high-resolution data will resolve the sphere of influence of a central black hole, and this will allow us to measure the black hole mass directly using gas kinematics. And this is probably the first time that we can do such kind of experiment beyond the local universe. And I will put my summary here. Thank you for listening, and I will be happy to take questions.
Great. Thank you so much, Minghao. Let's wait a little while for folks to enter their questions on Slack.
Okay, that's just a first comment, at least on your talk, saying that combining the high and low resolution data might be very interesting. Are you planning to do that?
Yeah, actually, this plot I'm showing here is a combination of the two. I mean, the low resolution data basically samples the overall structure and gives us a higher signal to noise ratio. Yeah, so our plan is to analyze the visibility of both low and high resolution parts simultaneously when all the data is collected.
Mm-hmm.
Okay, we have another question. In the Milky Way, we see intense starbursts and elevated star formation rates, even due to minor mergers, like 100-to-1 in stellar mass ratio. Those minor mergers drive pre-existing gas into central starbursts. Could this be possible for this source?
Yeah, that's a great question. Actually, we consider minor mergers pretty likely. Let me go back to the best fit lensing model here. So here, I'm claiming that surface profile can describe the emission pretty well. I mean, but there's a little bit residual, which contributes to several % of the flux. So that's why I say a surface profile works well. But you still see some residuals, which could indicate that there are some kind of small structures in the host galaxy. And we do consider minor mergers a very likely explanation to such kind of structures, and we'll definitely investigate more about that. And that's probably the task of the high resolution part of the program. And yeah, thank you for the comment. I think it's pretty, I mean, at least a very appealing scenario. Yeah, thanks.
Yeah, it'll be exciting to see that high resolution data in full for sure. So another question is, can differential magnification explain the misalignment between the major axis and the flux distribution and the rotation axis?
Well, I mean, well, it could be there could be some contributions to this issue. Say if the overall shape of the host galaxy is I mean, so if there's some bar-like structure at the center and is highly magnified, and that will kind of dominate, say if we fit a surface profile to the emission. So this kind of illustrates why we want a pixelized, a more detailed lensing model for this host galaxy. So that's for J/39. I think, yeah, differential magnification can play a role in this. And but regarding for the issue itself, I actually have I gather something from the literature that we can see these are just normal quasar host galaxy at high redshift. So this, as I said, this misalignment is pretty common. I mean, if you go through these plots, I saw like 30 to 50% of them have some obvious misalignments. That depends on how you define obvious. But I mean, this is a pretty common phenomenon in high redshift quasars.
That's fascinating. Well, hopefully, so we're out of time. Maybe you can answer a few more questions over Slack, Minghao. Thank you very much for a great talk.
Yeah, thank you.
So could you stop sharing, and then Sander and share. Yes, great. Okay, so Sander Schaus will tell us all about the Rebels program and first results from like ALMA. Yeah, take it away, Sander.
Thank you. Good afternoon. My name is Sander Schaus. I'm a PhD candidate at the Leiden Observatory. And today I'll show some results from the Rebels survey. So Rebels is a 70-hour large program on the ALMA telescope, targeting a large sample of luminous galaxies in the epoch of reionization. So why would you want to use ALMA for studying these high redshift galaxies? Why is ALMA an ideal instrument for this? Well, let's take a step back and look at some questions that we have about high redshift galaxies. For example, how quickly do they build up dust? How important is dust obscuration in these galaxies? How much star formation rate is hidden by dust? And we need to take account for that in our star formation rate census. And as you can see, the number of data points at high redshift is quite limited. Another thing is, how do we get spectroscopic redshifts? For most galaxies, we don't have spectroscopic redshifts, and that's because the universe is increasingly neutral and absorbs the Lyman alpha line, and basically taking that out of the picture. So we need to find another line that can take over that job. And finally, we would like to know the precise physical conditions where the star formation rate is taking place in these galaxies and how it's different from the low redshift universe. And it would, of course, be very interesting to know. A nice thing is, with ALMA, we can shed light on all of these points. So, for example, we detect the dust continuum directly. So we can directly measure the obscured star formation in these galaxies and their dust masses. And we have some very luminous emission lines. Specifically, the C+158 microline and the O388 microline are sufficiently luminous that you can blindly scan for them and get redshifts that way. And finally, there are a lot of emission lines in this part of the spectrum. And just like optical lines, you can use the line ratios of these lines to get constraints on the physical properties of these galaxies. So ALMA is really able to answer all of our questions if we want to use it like that. So this is nice in theory, but does it work in practice? And what we've shown in our pilot studies using this C+ line specifically is that you can blindly scan for this line and efficiently detect the spectroscopic redshift for a large sample of galaxies. And on the other side of the world, some Japanese groups have used the O3 emission line to also detect spectroscopic lines of very exciting targets at very high redshifts. So it's definitely possible to do this. And we want to do this for a much larger sample. And that's where Rebels comes in. So I've selected a sample of 40 sources between redshift 6.5 and 9.5. And we've searched a huge area on the sky, so 7 square degrees. And that means that we're scanning such a large area that's not really feasible to do with James Webb. So this sample is something unique, even after James Webb is launched, because our galaxies are so bright and so rare on the sky. And to be confident in our photometric redshift estimates, we use 3 independent people to do this. And then we design a so previously I shared that our pilot studies have mostly used the C+ line, and the Japanese groups have with great success mostly used the O3 emission line. So that begs the question, which emission line is better to use if you want to find the redshift of a source? And that actually depends on 2 things. So it depends on the line ratio you expect, and it depends on the atmosphere. So you can do a calculation and look at a line ratio from previous detections. So what we find is that O3 is in generally more luminous than C+. But because the atmosphere for C+ is a little bit better, it's actually more efficient to use C+ at lower redshifts. And that holds true up to about a redshift of 8.5. And then it's actually more efficient for the typical source to use O3. So that's the strategy we apply to our sources as well. So what we do is we do a spectral scan. And in practice, that means that you use ALMA to do different tunings, because the redshift coverage by ALMA and instantaneous tuning is quite limited. So you spend a lot of observing time actually looking at parts of the spectrum where there's no emission line. And you might think, well, that's a waste of time. But actually, that's not really the case, because C+ is much easier to detect than the dust continuum. So that means if you want to detect the dust continuum, you need to integrate a long time anyway. So a spectral scan is not really a waste of time. Actually, this is a very efficient method to both get a spectroscopic redshift, you get the emission line to probe the physical properties, and you get the dust continuum in one go. So does this actually work? Well, I'm glad to tell you that it works really well. What I'm showing here is a large, well, basically all our detections, and you can see that there are most of them have very high signal to noise. So what I show is the rest frame UV emission in the background. With the blue contours, we show the C+ emission, and with the orange contours, we show the continuum emission. And you see that for most sources, we both detect the dust continuum and the C+ quite at high significance. And you also see that there are some interesting things going on. For some sources, there are some misalignments, and for other sources, everything is very well aligned. So this is definitely something we're looking at in more detail. So let's take quickly a look at some of the statistics of our detection. So does the spectroscopic redshifts we find agree well with the photometric redshifts? Well, luckily they do, as you can see in that figure. There might be a slight bias at high redshifts, but that's not really, well, we're looking into that in more detail. So looking at the fraction of sources we detect as a function of UV star formation rate, you can see that for high star formation rates, we detect most sources. And this becomes even more apparent when you include the obscured star formation rate. So if we look at the total star formation rates, not only the UV, then for our sensitivity limit, we basically detect, well, by far the largest, the majority of sources, despite the fact that we're only using spectroscopic photometric redshifts. So our survey is working really well. And we've created a very interesting and quite large sample of interesting sources. So what can we do with that? Well, one thing we can look at is, for example, the kinematics of these sources. And what we see is that for a significant fraction of our sample, we find quite clear velocity gradients. Now, this enables us to look, for example, at the effect of rotation versus dispersion support in these galaxies, and maybe even at mergers. But you should keep in mind that this is very low resolution data, and that's actually the limiting factor of our data at the moment. So we've created a model that fits the data cube in 3 dimensions for a rotating disk model, a thin rotating disk, and a merger model. And what we find is the residuals for both these models are quite similar. So it's not really possible at the current resolution to tell both scenarios apart. But nevertheless, we'll be able to provide at least some insight into the fraction of sources that's dispersion versus maybe rotation or merger, and also their dynamical masses. Something interesting that we observed and completely didn't expect is that next to our target sources here in the middle of our field, we find that there are additional sources, so at the same redshift, that are nevertheless completely obscured in the rest frame UV. So that's something quite strange. These sources are not extreme. Their star formation rates are not extremely high like ULURCs or or SMGs, but nevertheless, they're completely invisible in the rest frame UV. And we even have HST observations for one source and still invisible in even those deep observations. So that means that with the current observation, surveys that look at that try to make a census of the star formation at high redshifts, we might be missing a significant fraction of the sources. And this is discussed in more detail in Yoshi's Fudamoto's paper that's upcoming. Okay, finally, I want to show some results from the pilot. We're still working on the Rebels analysis for this, but we're not really limited by the number of data points. So what I show here is the IRX beta relation that we often use to correct UV-based star formation rates to include obscured emission. So it's really important that we understand this well to take proper sense of the total amount of star formation going on at high redshifts. So we would like to quantify that, and one way of doing that is fitting it, but one big assumption comes in here, and that's the assumed dust temperature of your SED model. And what I show here is that the assumed dust temperature has a huge effect on the fit you get. It's more quantified here. So this is the slope of the dust attenuation curve. So that's what we use to correct the observations. And if you use a dust temperature of 40 Kelvin, and well, it's also dependent on the intrinsic beta slope. So if you assume intrinsic beta slope and you also assume a dust temperature of 40 Kelvin, it's mostly consistent with SMC. But then if you move to higher dust temperatures, it becomes consistent with Calzetti. So there's a huge difference between this. And the same goes for the dust masses. If you want to understand how the dust mass is formed, for example, through supernovas or maybe grain growth in the ISM, then we need to understand the total dust mass, and that's not really possible without understanding the dust SED. So our current understandings really hold back by our lack of understanding of the dust SED, and we need more observations to solve this issue. Okay, so finally, I want to conclude my presentation by showing showing some things we're working on and some papers we're working on. So we're of course looking at the dust law and the evolution of dust. We're looking at kinematics. We're looking at the far infrared and C+ luminosity functions. We're also looking at C+ halos and outflows and much more things. We're of course also working on a public data release. You can see the concept website here. Hopefully that's coming soon. And I would like to emphasize that our sample is an ideal list of targets for follow-up observations. So I already showed that we really need higher resolution observations to understand the kinematics of these galaxies. And we've done that for one source in our pilot, and you can see the amazing improvement we get. And of course, to understand the variety in galaxies at these redshifts, we need a larger sample to be able to understand this. Also, the O3 line is an ideal target to follow up. So if you target C+ and O3 and the dust continuum for both of them, you get a much better insight in the conditions of star formation. And that's probably, well, Joris is gonna talk about this in the next talk. So that's gonna be really interesting. And also the nice thing with targeting O3 is that for you basically get the dust continuum for free. So there's the dust continuum point at about 90 microns. So that's closer to the peak of the dust density. So you get a better idea of what the dust temperature is. And besides that, there are, of course, other emission lines that you can target, like nitrogen and oxygen. We have also approved very deep observations on the CO line for one of our galaxies. So we'll be able to constrain the gas content in that galaxy, hopefully really well. And yeah, that's on the JVLI telescope. As Mauro previously showed, for a large fraction of our sources, we will also be receiving IFU observations at R of 100. So we'll be able to probe the UV and optical spectrum from Lyman alpha to H alpha and connect that to the ALMA observations. It's going to be very interesting to see what comes out of this. And finally, we have also a lot of incoming ground-based data on Lyman alpha line and metal lines in the rest frame UV to maybe also constrain something like the AGN contribution in these galaxies. So I hope I was able to transfer some of my enthusiasm about this very exciting survey in this presentation. I would like to thank you for your attention, and questions are very welcome.
Great. Thank you, Sander. So we'll probably have time for one quick question if y'all want to type it in, and then we'll move on after that.
Yeah, there's a quick question here. What is the effect on your conclusions because you're using a UV selection of your targets?
Yeah, of course. That's a limitation in our sample selection. Of course, it's the best we can do at the moment, right? So, but I agree, it's a limitation, and we're working with simulators, and we're looking at ways of properly estimating the completeness of our sample and doing things like that. Yeah.
Yeah, it's really beautiful data, and it's just exciting to see. Obviously, it's a good starting sample. So cool. All right. Well, we're out of time for Sander's talk, but please feel free to pepper him with questions in Slack some more. And with that, we will move on to the next talk by Joris Wittstock, who is a student at Cambridge, and he will be telling us about uncovering physics of star formation in the EOR with C2 and O3.
Yeah.
Take it away.
Thank you very much, Caitlin. And yeah, my name is Joris Wittstock. I'm a third-year PhD at the Kapley Institute in Cambridge. And yeah, today I'll be talking about looking at C2, as Sander has just nicely introduced for me with ALMA, but also the O3 line at 88 micron. So very briefly, we've all seen this overview many times now, and I'd just like to point out again, so before James Webb, of course, the rest frame optical were really limited to the lower redshifts. And then even if you go to the rest frame UV, where we have, of course, the brightest line being LAM and alpha, this starts being absorbed at redshifts of about 6 or 7. But already with ALMA, we can perform these spectroscopic studies at high redshift, well into the epoch of realization, using the mainly C2 and O3 lines above redshifts of about 4 and 6. And what's more, if you use ALMA, you actually get spatially resolved spectroscopy. So you can make these beautiful velocity maps, for example. So the sample I'll be talking about today consists of 4 galaxies. And so rather than being spectroscopically confirmed with LAM and alpha, as Sander has just explained, these have been confirmed with C2 using ALMA. And so what are these systems like? Well, they're quite UV bright. They're normal star-forming galaxies, so star formation rates between about 20 to 60, and stellar masses of between 1 to 4 times 10 to the 9 solar masses. And you can see 2 of the SEDs on the right here. So I'd just like to briefly mention, again, the selection technique involved using the medium to high equivalent widths in the optical, rest frame optical, to allow the Spitzer photometry to really get a narrow constraint on the photometric redshift before scanning with ALMA. So then on top of the ALMA data, we also obtained Hubble rest frame UV imaging for 2 out of the 4 sources. And so what can we start to see? Well, I'm showing the O3 contours here on top of the rest frame UV. And you can see the O3 line traces the rest frame UV quite well, but there's not a perfect one-to-one match. And this is the same in the other 2 sources. And then finally, so in our sample, we also simultaneously get a detection on, or a constraint on the dust continuum at 90 microns. And so we don't actually detect any dust for any of the 4 sources, but this does give us some really interesting constraints. And I'll talk about that at the end of the presentation a little bit. So, so with this sample then, we have 2 traces of the ISM. And so first of all, the existing C2 data traces the neutral part of the ISM, while oxygen-3 is only really produced in more highly ionized gas. And so, as Sander already mentioned, what we can look at then is, for example, the line ratio. So oxygen-3 over C2, I'm showing you here in two of the sources. So for example, in this source, we can already see across the source, the ratio changes from this gray region where we see ratios of about unity all the way up to ratios of about 10 and even higher. And we can resolve this to the beam size, which corresponds to roughly 2 kiloparsecs at this redshift. But at the same time, we also see for other sources, for example, this one, just a generally quite low ratio of somewhere between 3 and 4 for this particular source. So we can start to compare our measurements with some reference samples then. So here I'm showing you the line ratio as a function of star formation rate. And well, two main reference samples that we have at low redshift are the dwarf galaxy survey, which consists of metal poor dwarf galaxies, and then as well a sample of local ULERGs. And then the high redshift galaxies are the colored points in the top right here. And so these all occupy a slightly different space of this plot. So we can start to wonder, are their ISM properties actually systematically different? But so one thing we found is if you look at the same ratio, but now as a function of the equivalent width in the optical, so oxygen-3 and H beta, we see this general trend both in the dwarf galaxy sample as well as our high redshift sources. And so we even see that if you just take the subsample of dwarfs at higher equivalent widths, there doesn't seem to be any obvious difference. And secondly, if we use a simple nebular model, we can see that we can reproduce the values we see for our systems with a young, so about 1 megayear burst of star formation and a sort of moderate ionization parameter between about -3.5 and -3. And finally, we're currently still working on trying to see if we can, for example, explain some of the spatially varying line ratios that we see in our sources. So just the last part I'd like to spend on what we could say about the dust with our measurements. And so as we've already heard from Rebecca, dust is really a key ingredient in galaxy evolution. And so it helps in forming molecular gas, but of course also it crucially obscures star formation in the UV and optical. So what can we learn by looking at dust at high redshift? Well, first of all, I think what's really interesting is just because these systems are, we see them at a time when the universe was so young, they simply haven't had a lot of time to actually form their dust. And so we can start to compare the amount of dust we see to what is theoretically expected from models, for example. And secondly, what we also expect to see, which we've already heard about, is higher dust temperatures. So this is just comes down to higher specific star formation rates, where if you have more massive stars heating up their surrounding dust, then the hot dust becomes this more dominant component of the whole system. So what do we actually see? Well, we, of course, then have two constraints on the dust continuum, both coming from the existing C2 data and then our new upper limit at the 90 micron regime. And so I would just want to highlight this specific source. You can see our non-detection combined with a very significant detection at longer wavelengths, we can actually rule out a lot of the higher temperature dust templates. And so for this specific source, we see that peak temperature must be somewhere below 40 kelvins. So if we start to compare that to other measurements in the literature, this kind of fits in. So as you can see from lower redshift, we do see this general trend of higher dust temperatures towards the higher redshift. And so this is the measurement I was just showing you. And we do see this is just about in mild tension with some of the even more conservative trends we might expect. But I think the only thing we can really conclusively say about this is that there's just no clear picture at high redshift yet. And that's just mostly comes down to, most of these systems only having at most 2 or 3 photometric data points. And so as Sander already pointed out, we just need more measurements. So just one final point then, this low dust temperature in the system actually then requires a significantly, relatively quite high dust mass. And combined with the also relatively low stellar mass, we then can convert this into a dust yield. So how much dust mass is produced per dust producing star, which results in this number of up to about 4 solar masses. And this is tentatively higher than where you would expect the maximum yield to be from AGB stars and supernovae. And so this might be, for example, the evidence for growth of dust grains in the ISM, which is quite exciting. And that brings me to my conclusions. So presented 4 new detections of the oxygen 388 micron line in normal star forming galaxies at redshift 7. We find a tentative trend with the equivalent widths of optical lines, and finally we see quite surprisingly low dust temperatures, which may hint at dust formation by grain growth. So thank you very much, and yeah, looking forward to seeing any questions.
Thank you so much, Joris, for a great talk. We'll give people a little time to enter questions in the Slack.
Okay, here's the first one already from Sarah Bosman. Do you see any velocity offsets between C+ and O3 subemitter lines?
Yeah, that's a good question. Not any major velocity offsets. So I've got all the spectra here, red being the O3 line and blue being the C2 line. So for example, in this source, you see a slight velocity offset, but mostly they generally agree quite well.
So while we wait for, oh, okay, here's the second question from Rebecca. What is the resolution of your C2 and O3 data? Is there any way you could be resolving out extended emission?
Yeah, that's also a great question. The whole measurement set is quite heterogeneous. So for these 2 sources, we've got slightly lower O3 resolution, but slightly higher C2 resolution. But we do also have the initial low resolution C2. And then for these sources, we have slightly higher O3 resolution, which may resolve out some of the emission. But yeah, there's not a lot of evidence for that because we do see it's quite clustered on top of the rest frame UV.
So we have another question. Are there any AGN signatures in your sources, and do you have rest frame UV spectra?
That's also a very good question. I would have to double check. Not that I know of, but let me get back to you on that. Yeah.
Okay, great. Yeah, feel free to answer it in the Slack later. And I just have a really quick question on your SED. Fits to the interesting result that you're finding lower dust temperatures. I saw that you have some emissivity spectral indices that are pretty low, like as low as 1 in some instances. Could you speak about the choice of beta IR there?
So what I actually do here is I just take templates from any temperature and then allow the beta to vary between 1 and 2.5. And then the non-transparent models are actually just the values that are allowed within the limits. So say for this temperature, it's barely allowed, but only if you take this very low beta value, if that makes sense.
Right, yeah. But yes, then the flux could be lower, of course. yeah, cool, great. Well, it's time to transition now. So thank Joris again and pepper him with questions in the Slack. And next up, we have Seiji Fujimoto. So good. Transition to Seiji's slides. Seiji will be talking about the ALMA lensing cluster survey today. So take it away, Seiji.
Okay, so hello everyone. First of all, thank you, organizer, for introducing me and giving me this wonderful opportunity to be here. So today I will talk about the great outcome from ALMA large project called ALMA lensing cluster survey, especially about the first achievement of spatially resolved ISM study for a typical sub-Earth galaxy at redshift 6. In the later part of my talk, I will also introduce about our JWC program scheduled in cycle 1 related to this ALMA survey. So first, the motivation. The early galaxy evolution is regulated by several key mechanisms taking place in the ISM, such as clump and disk formation, stellar feedback, and mass building via star formation and mergers. To address such a detailed ISM picture of early galaxies, recent ALMA studies have detected the ionized carbon emission, which is one of the helpful Coulomb lines tracing the cold ISM. But a large diversity has emerged. Some are brightly detected, while others are not, or sometimes it shows significant offset from the stellar continuum. Several causes have been discussed, but one important fact is that ISM property can be largely different even within a galaxy. So here is the high-resolution ALMA line observation towards SDT81, a famous strongly dense dusty Cerberus galaxy at redshift 3. And it also finds that line luminosity normalized by finite variety continuum varies by almost 2-deck scale within the galaxy. So although ALMA has nicely offered the line detection from early galaxies, now we should move on to spatially resolve this detection, characterize the localized physical property of the ISM, and understand what the key mechanism is taking place in a typical galaxy in the early universe. To overcome such a small size and faint property of such typical early galaxies, the gravitational lensing is essential. So including this context, a large unbiased ALMA survey has been carried out. Using 100 hours of the ALMA large program time, we map out 33 massive lensing clusters by setting up 2 frequency tuning, which maximize the detectability of not only the continuum sources, but also the line emitters. And we achieve a total area of 100 arc square minutes with a moderate data depth, but the average sensitivity after the lensing collection is almost comparable to the previous deepest ALMA surveys. So here we compare the area and sensitivity of the ALMA large surveys so far performed. So after the lens collection, the parameter space in our ALMA survey is like this. So ALMA lensing cluster survey explores the faintest regime, both in the depth and area, which provides us with unique objects that couldn't be identified in previous surveys. Moreover, independent line of sight towards 33 massive lensing cluster are helpful to overcome the cosmic variance. As a result, we are identifying the hundreds of continuum sources, tens of line emitters, and even several lens near-infrared dark galaxies that are bright in ALMA, but are not detected at all in all HST band or even sometimes Spitzer IRAC bands in some cases. And what is more, we discovered very interesting bright cis-line emitters at redshift 6, which is the main topic of my talk today. So here summarizes the ALMA spectra and the line intensity in red contour overlaid on the HST map. So we detect these two bright line and one tentative line at the same frequency, exactly at the position of redshift 6 Lyman break galaxies. These LBGs show a similar SED shape, and the peak of the redshift photometric redshift distribution are in excellent agreement in the case that the line is interpreted as the C2 line at redshift 6, shown in the red line. In fact, this redshift solution is confirmed with the latest GMOS spectroscopy, where we see the continuum break at the expected wavelengths. So we determine the redshift, and based on this redshift solution, our independent mass model consistently predicts that these LBGs are multiple images from one galaxy. So based on these results, we conclude that these bright lines are multiple images of the cis-line emission from a galaxy that, at redshift 6 behind the cluster. And remarkably, not only the cis-line, the observed H-band magnitude is also one of the brightest so far confirmed at redshift over 6 among the star-homing galaxies, so suggesting that this system will be a unique laboratory for detailed study in the early universe. So we investigate the intrinsic property of this unique system. So assuming a celsic profile and fitting routine between the image and source plane, we find that a subregion of the galaxy is crossing the caustic line, which is stretched out to the elongated shape observed as the arc, while the other multiple images traces the whole region of the galaxy in the source plane. The magnification factor is estimated to be around 20 and even 160 at the arc. Also, such high magnification has large uncertainty in general, but it is not the case in this system with two reasons. First, the configuration of these multiple images works as a strong constraint, so the estimate wouldn't be easily changed. And second, we confirm these interpretation and magnification values with independent 3-lens models constructed by 3 independent modelers in our team. So we think that the high magnification values in this system would be much more robust than usual. So here summarizes the physical property of this system after the lens correction. So 3 times fainter than the characteristic luminosity, both sub and 4 regions of the galaxy are falling on the main sequence of star formation and stellar mass dilation. And based on 3D modeling results, we also obtained the dynamical mass and subsequently gas mass by subtracting the stellar mass from dynamical mass estimate. The gas mass and the galaxy size estimate shows the average value among the typical star-forming galaxy at redshift 6. So we conclude that this strongly dense galaxy is an abundant and representative population of the sub-L-star galaxy at redshift 6. To see the direct observed picture in the source plane, we also performed the pixel-to-pixel source plane reconstruction. First, for one of the multiple images which trace the 4 regions of the galaxy. Since we find several clamp features there from the HST map, those are marked from A to D. And the right panel shows the source plane reconstructed map. The white ellipse here corresponds to the source plane HST resolution, showing that we achieved a few hundred parsec scale resolution in the source plane. Next, for the arc, we obtained the reconstructed map presented in this inset panel, where the lens corrected luminosity reaches down to about 1% of the bright peak of the whole region. Interestingly, we find that this luminosity distribution from the arc perfectly matches with the position of a faint clamp seen here, WE. So this, this is away from the UV brightest peak by 1 to 2 kiloparsec from the brightest peak of the galaxy. So this nicely illustrates the power of the lensing, making even the faintest outskirt emission highly visible, which is almost invisible in the reconstructed map from other multiple images, even with the magnification factor around 20. The cis-line distribution are also reconstructed and find that its effective radius is 2 to 3 times more extended than the left plane UV one, while the cis-line peak positions are consistent within the errors from the UV peak position. both in sub and four region of the galaxy. So based on the current data depth and resolution, we conclude that the majority of season line arises from the redshif frame UV emitting regions. Thanks to this unique system, we investigate the spatially resolved seed line and star formation relation. So after the lens correction, we find that both sub and four region of the galaxy show the relations consistent with the local galaxy relation within the dispersion. We also measure the redshif frame UV sizes and plot the seed line over the star formation ratio as a function of the star formation surface density and compare with another spatially resolved results obtained from the dusty starburst galaxy at redshift 3. So these plots are known to have an anti-correlation, which is explains that the abundance of singly ionized carbon and its emissivity are saturated in the highly ionized state region at the high star formation and surface density region. We find that subregion shows a slightly higher value, which is consistent with this known trend. So this slightly higher seed line emissivity in the subregion of the galaxy would be explained by the sufficient offset from the UV brightest center, which makes the ionization state at this subregion keep moderate. So we have studied the cold ISM property with ALMA. So what's next? We are really happy to be informed that our follow-up JWST program targeting two brightest multiple images is approved in cycle 1. So by using the near-cam deep imaging and near-spec IFU, and thanks to the brightest property so far confirmed at redshift over 6, we will achieve the full characterization of early galaxy assembly with ALMA and JWST. The full means that we will study from young all-star population that's obscured and obscured star forming regions, cold and hot ISM, and also the dark matter components. So here we break down in 3 key goals in the JWST program. First, the detailed structure. The detailed structure of individual star forming clump will be investigated down to 20 to 80 parsec scale resolution in the source plane. And the second, we study the spatially resolved internal physical property of a typical star galaxy at redshift 6, such as BPT, electron density, and the metallic gradient. So this spatially resolved characterization will be important itself, but it will also provide the key insight on what physical mechanism causing the large diversity in the seed line property, for example. And third, we will study the detailed kinematics by using a bright optical line from ISM to the circumgalactic medium scale, including the motion of individual clumps in falling and outflowing, and also testing if there is a drop in the rotation curve at the outer area, which constrains the dark matter concentration in a typical galaxy at redshift 6. So in this way, also with the ALMA data, we will fully characterize the representative sub-Earth galaxy at redshift 6. So please stay tuned. So here is a summary. The ALMA lensing cluster survey is uniquely exploring the faint 1 mm regime and discovered a strongly lensed multiple image seed line emission from a representative sub-Earth galaxy at redshift 6. The HST and ALMA images map out the structure down to a few hundred parsec scale in the source plane, and the formation relation and relation is consistent with the local galaxy from spatially resolved and full galaxy scale. And JWST program is also scheduled, and we will fully characterize the key components of the galaxy, early galaxy, also together with ALMA. So stay tuned, and thank you for listening.
Great, thank you so much, Seiji. So let's give folks a little time to ask some questions, and then we might have only time for one before we move on.
There's one question in general. How many more sub-L-star galaxies do you expect to find? I don't know, I'm assuming in your data set.
So for starburst galaxies, sorry, C plus emitter?
Sub-L-star galaxies, if you can detect any.
In terms of the redshift, intermediate redshift, we also identify many long arc-shaped, elongated shaped lens galaxies. So we will, let's say 10-ish strongly lensed continuum sources we already identified. But in terms of the such strongly lensed C plus emitter, at the current stage we only have one.
Great. it's really beautiful data on this source. So please, if you have more questions for Seiji, please put them in the Slack. And we might take this time to transition to our last speaker. And Seiji, you can answer any more questions. I'm sure they'll come in.
Yeah, thank you.
There. Thank you, Seiji. Okay, the last speaker of the conference in the day, Srivani Jarugula, who's at University of Illinois, working with the SPT collaboration. Yeah, you're going to share with us some results on Redshift 6.9 dusty galaxies. So take it away.
Thanks, Caitlin. I'm Srivani Jarugula, a final year PhD student at University of Illinois, Urbana-Champaign, and I'm part of the South Pole Telescope Sub-Millimeter Galaxy collaboration. So in this talk, I'll be presenting our analysis on molecular line observations in 2 dusty star-forming galaxies at Redshift 6.9. Before moving on, I would like to thank all the organizers for giving me this opportunity and everyone who has managed to stay until the very last talk. A little bit of an introduction on this really interesting source, SPT 031158. It's a pair of lensed galaxies at Redshift 6.9, which is less than 800 million years after Big Bang. And this is one of the most distant detection of dusty star-forming galaxies in literature. Like I said, these are a pair of gravitationally lensed galaxies labeled as West and East. West is magnified by a factor of about 2.2, and East is barely magnified with a magnification of about 1.3. So in the image, in green is shown the HST observations, and in red are the ALMA 160 micron observations. So we detect UV emission from East, but we do not have any detected UV emission from West. And the green source that you see on the right side of the plot is actually the emission from the foreground lens. Both the galaxies are extremely luminous with really high star formation rates. And this is actually comparable to luminosity of other high redshift sub-millimeter galaxies and quasars above redshift 6. And most of this luminosity is coming from star formation, as there is no AGN that is detected in these galaxies. Here are some of the recent observations and some of the published observations on this source. On the top left is the high resolution ALMA 160 micron continuum, and you can see the clumpy nature of both the sources at this high resolution. And the O3 and C+ analysis is presented in Moroni 2018. And from the C+ and O3 ratio, we can see that these 2 galaxies are physically a little bit different looking at this ratio and also looking at the C+ to LFIR ratio. In addition to these 2, in addition to the O3 and C+, we also have unresolved molecular CO observations presented in Stranded 2017. And by unresolved, I mean the West and East are not separated. So in this analysis, we present resolved mid-J and high-J CO transitions at a resolution of 0.3 to 0.5 arc seconds, which corresponds to about 1.6 to 2.7 kiloparsecs at this redshift. We also have a detection of a water transition, and this is the most distant detection of water in a star-forming galaxy without an evidence of an AGN. So on the top panel, the background is ALMA continuum emission, and the contours are the moment zero contours of the molecular lines. And the bottom panel shows the spectrum in West, which is shown in blue, and in East, which is shown in green. Okay, so what information are we getting from all these molecular lines? it's really important to understand the molecular content of a galaxy to really know the star formation rates going on in these dusty star forming galaxies. But molecular hydrogen is really difficult to observe. So the next best option is to observe the carbon monoxide molecule, and the different transitions of CO are tracing different regions of the galaxy. Another good alternate tracer to CO is neutral carbon line, which is not as prone to photodissociation as CO is. And it has been observed that the luminosity of neutral carbon is actually highly correlated with the low JCO transitions. So that makes it a good gas tracer. And water is also a really abundant molecule in the universe. And it has been shown in the literature that there is a tight correlation between the water and infrared luminosity. And this correlation extends over more than 3 orders of magnitude, as shown in the plot on the right. Sorry. And so because these galaxies are gravitationally lensed, we perform a visibility-based lens model by assuming a source plane structure like a Sirsic or a Gaussian profile. And here's an example of how the lens modeling looks like. Okay, moving on to the results. So we look at the correlation between the water transition and the far infrared luminosity. And it's been shown in the literature that this transition is a good tracer of far infrared luminosity, which holds true at redshift 6.9 in this source. Because of this relationship, water can be used as a star formation rate calibrator. And when we compare the spectral line energy distribution in 0311 with the other local and high redshift star forming galaxies on the left, and with the local AGN and high redshift quasars on the right, we see that the SLED peaks at the mid JCO transitions as expected of the high redshift submillimeter galaxies, unlike the high redshift quasars, which peak at a higher JCO. And when we look at the ratio of the high J to mid JCO and compare it with the local starburst and AGN and high redshift ULUGs and quasars, we find that the CO 10⁹ to 6:5 ratio is actually comparable to low redshift AGN and high redshift quasars. Although we cannot infer the presence of AGN from this plot, we can say that in addition to photoelectric heating, there are other heating mechanisms, probably something like X-ray heating from AGN or even mechanical heating from AGN or stellar activity like stellar winds or supernovae explosions or mergers. Given that we have these multiple CO transitions and also a really good coverage of photometry, we perform a radiative transfer modeling, and we model the dust, CO, and neutral carbon together. And some of the parameters we estimate from this modeling are gas densities, dust and gas mass, temperatures. Here is how the modeling looks like. So the first panel is a single component radiative transfer model where we assume that the ISM consists of just one component. In the middle, we have a 2-component model. So the blue is tracing the cold diffuse component, while the red is showing the warm dense component of the ISM. And in the bottom panel is a turbulence-driven radiative transfer model, which is a more realistic representation of the ISM. And in this model, we are sampling about 50 gas densities from a probability distribution function. And from the modeling in West and East, we can see that our models reproduce our observations pretty well. So from both the observations and modeling, we can estimate properties of these galaxies, such as gas mass and CO luminosity, from which we can calculate the gas mass conversion factor. So one way we get the gas mass is from the radiative transfer modeling, but there are other ways of estimating gas mass. And one of the methods we use is to calculate gas mass from dust mass, which we get from SET fitting and assuming a gas to dust conversion factor. And we can also calculate, gas mass from the observed neutral carbon emission line that we observe in 0311. So alpha CO is, traditionally it is assumed to be 0.8 in new logs and about 4 in main sequence galaxies. However, there is like a lot of discrepancy in the value of alpha CO. It can range anywhere from 0.4 to 6, depending on what assumptions go into your dust estimates and your gas estimates. So on the left, we have alpha CO on the y-axis and far-infrared luminosity on the x-axis. And there is a lot of scatter in the alpha CO values in high redshift sub-millimeter galaxies. And 0311, the alpha CO estimated in 0311 from all the different methods, it lies within that scatter. On the right is this dust temperature on the y-axis, and we see a statistically significant correlation between alpha CO and dust temperature in the SPT SMG sample. And such a correlation has been observed in main sequence galaxies, as discussed in Magnelli 2012. When we can calculate the depletion time as a star formation rate over gas mass. And from this plot on the right, we see that there is a slight evolution of depletion time with redshift up to redshift 3. And such a trend has been observed in main sequence galaxies. But beyond redshift 3 up until redshift 6.9, we do not see any sort of evolution in depletion times. I will leave you with the summary slide. We have more analysis and more observations coming out of this source, so please stay tuned for more. Thanks.
Great, thank you so much, Srivani. We'll wait for a few questions to come on Slack.
Okay, here's one about, since these are high redshift galaxies, the person is wondering if it's necessary to consider cosmic ray ionization in your analysis, or maybe you can just include this as a mechanical heating.
Yeah, that's a really good question. It's important to consider all these effects at high redshifts. So the radiative transfer modeling code that we use includes kinetic temperature to dust temperature scaling, and it's a free parameter. So that could vary based on any sort of mechanical heating or cosmic ray heating. That parameter is free to vary. So we are considering all these effects in the radiative transfer modeling, but we just don't separate them into cosmic rays or mechanical heating.
So while we wait for other questions, I was going to ask one, and perhaps you said this, and I'm sorry. So obviously the SPT sample in general has a remarkable suite of observations to constrain molecular gas, arguably better than any other sample we have at high redshift. And you have all of these tracers. You have dipping into lower J. And you have the C1 and you have the dust continuum. So in your constraints on alpha CO, I imagine you kind of take all of that information into account, and dynamical constraints too. Was that alpha CO that you measured just for SPT 0311, or was that aggregate for this whole sample of SPT sources, or are they similar? Can you comment on that?
Right. So one problem with alpha CO is that in literature, like everyone uses different assumptions, right?
Yes.
In calculating alpha CO. A few of them get it from dust masses, like some of them assume a gas to dust mass ratio of 100 or above 100, depends on the metallicity or dynamical mass, or even like scaling relations, right? If going from CO3 to 2, say 1 to 0 or something. So to avoid all that, what we did is we recalculated everything using we recalculated the dust masses, so refit the SEDs assuming the same beta value. And using a gas to dust mass ratio of 100, we calculate the gas mass for all the sources on this plot, including the low redshift and the high redshift sample, just to get them on a same scale when we are comparing.
Mm-hmm. Mm-hmm.
Yeah.
Cool. Thank you. Okay, we have a question. May I ask the temperature of the cluster where you observed? Not entirely.
So
certain what cluster, but
well, the SPT sample in general has a higher dust temperature, because it has higher specific star formation rate. So these are mostly like biased towards higher dust temperatures.
Yeah, I guess we can see on this slide here the range of dust temperatures probed, with the gray points being the SPT sample.
Yep.
Great. Well, I would say any other questions for Srivani can be dumped in the Slack, and you can all have a great conversation about SPT 0311 and all of the dusty sources from this session. And this concludes SAZERAC 2. Steve, do you want to say anything before we?
Yeah, thank you. Thank you, Caitlin and Pascal, for running this final session. So we just have a few closing remarks. So on behalf of my co-chair, Steve Wilkins, and the entire SAZERAC 2 SOC, I want to thank you all for attending and presenting and making this conference successful. We heard, I believe, 60 extremely excellent, exciting talks, mostly from junior people in our field. And it really shows that the future of epoch of reionization science and analog science and everything we heard about is really, really bright. Especially with JWST coming and the immense amount of cycle 1 data coming, but there's a lot of exciting observations and modeling going on. To put out another thank you to the SOC for helping to organize, many folks there, and give special thanks to several graduate students who helped behind the scenes make this possible, including Will Roper, UC Cusisto, Ashwin Vijayan, Rebecca Larson, Katie Tworowski, and Oscar Chavez Ortiz. The Slack will keep going, keep chatting. We don't pay for it, so it only keeps the most recent 10,000 messages, so that can hopefully keep us going for a little while. So please continue asking questions. There are various channels on there that are relevant all year round. You can advertise jobs, you can advertise new papers, anything you like. So please keep that going. The recordings are already on YouTube, so each session is there, and individual recordings for each talk will be on the website in the next couple of days. That takes a little bit of time. And please stay tuned for emails about future events, including more SAZERAC SIPs. Those were those short, 1 or 2 afternoon conferences that I think we've done 5 or 6 of them by now on various different topics, and those seem pretty successful. We'd like to keep that going. And yeah, that's it. Thank you all again. And I hope to see you all in person at an in-person conference soon. Take care.
I just thought I'd say thank you everybody again for listening. It was really great conference again. Hope everybody enjoyed it.